Okay, so I created for you guys a fake data set, and I just wanted to take a moment to orient you to this database. So this has 60 participants in it. Participants are male and female, which I have in this column here. I then have a column where I code by gender. Ones are female and zeros are male. And then I have an income column in dollar units. And then I have another column that describes mom's level of education. You can go to the values part in variable view to see what these different numeric codes mean. So this is a ordinal scale where 1 is high school degree, 2 is mom has college degree, and 3 is that mom has a graduate degree. I then further coded this to ones and zeros, for 0 being just college and 1 being anything after that, or sorry, 0 being just high school and 1 being a college degree or beyond. And then I have a within subjects variable. So in this hypothetical data set, we looked at each of these participants 3 times, once at 18 months, once at 24 months, and once at 36 months, and assessed the vocabulary of these kids at these 3 different time points. The range of these roughly follow what I was able to find online for kids' vocabulary development across this time. And so the lesson that I want to go over for this video is to talk about correlations. So in class we talked about 3 kinds of correlations that you could do. The first one is a Pearson product moment correlation. That is probably the correlation with which you are most familiar, and it measures the association between 2 quantitative variables. So here we have a variety of quantitative variables. Income, for instance, is obviously something that is numeric and varies on an interval type of scale. Vocabulary at these 3 time points would be as well. And then these are examples of more like categorical variables, though you could argue that this is an ordinal variable. Gender is clearly a categorical variable. For the purposes of this, we'll treat mom's education coded as a categorical variable. Okay. All right, so to run a basic correlation, we just go to Analyze and then Correlate. We're going to run a bivariate correlation. So bivariate, again, means 2 variables. It's a little bit of a misnomer here because we can actually put more than 2 variables. So let's just look, for instance, and see how vocabulary correlates over time. So we'll put these 3 time points of vocabulary in here, and I'm going to go ahead and push OK. And here is an output table. You'll definitely need to know how to interpret this, these kinds of outputs. So we can see that there's a Pearson correlation on the top here. And this is our first variable of vocabulary at time 18 months. So the top row corresponds with the lowercase r, or Pearson correlation. The second row corresponds with a p-value. And the third level, the third row here, corresponds with the n, or the sample size. Okay, so here we have the correlation between 18 months vocabulary and vocabulary at 24 months being positive and a weak relationship. It is statistically significant. So the greater the vocabulary at 18 months, the greater the vocabulary at 24 months. That tends to be the case. And there's an even stronger correlation, although I really should not say there's an even stronger correlation because we would need yet another test to compare this 0.327 and this 0.479. So instead I will just say that there is a correlation also between vocabulary at 18 months and vocabulary at 36 months. And that relationship is small to medium-sized correlation. and the p-value here is reported as 0.000, but we should never report a p-value as 0 because there is always some probability that you could find this result, even if the results were not true. So when we double click in here, it may give you the actual p-value, you can see, is 0.000107. Instead of reporting that, though, anytime we see these 3 zeros like this in the table, we can just say p is less than 0.001. That is the convention. Otherwise, we will report p-values as up to 2 digits. So here we would say p equals 0.01. Okay? Moving on to the second row, we can see that this correlation here is redundant with this correlation. So vocabulary at 24 months correlates with vocabulary 18 months. We've already talked about that one. But vocabulary at 2 years old also correlates with vocabulary at 3 years old. Here the correlation we would is 0.689, but we would just round that and report it as 0.69, and then p is less than 0.001. And then finally, we can see that this final row is fully redundant with the 3 correlations that we've already looked at. So one of the ways that you might look at this correlation table is to look across the diagonal and look only at the top part of the diagonal or only at the bottom part. These are mirror images of each other. Okay, so that's a Pearson correlation. The other kind of correlation that we would talk about in class would be a point by serial correlation. These correlations are those that relate a quantitative variable and a categorical variable. All right, so here in our data set, going back to our data set, we might look at something like the relationship between gender and the relationship between vocabulary. So I just want to show you that this first column of gender I have as a string variable. Under variable view, you can see that it's set up as a string variable, which means that within these cells you can write letters. You don't have to write numbers. If your variable is set up as numeric, as the rest of these variables are, then SPSS is going to expect that the value you put in there has to be a number, and if you try to put something like the letter F here, it rejects that as a possibility. Okay, so I tried to push F and enter, and it maintains that the value has to be numeric. All right, so what I want to look at maybe was the correlation between gender and vocabulary, and I want to go through an example with you where we would look at gender as this numeric, as this string variable. So you can see that gender code actually doesn't even come up as a possibility because you can't correlate a string variable with any other variables. So I'm going to look at this gen code variable, which actually is fully redundant except for we code it into a number, which will allow us to run a correlation. So again, we can't correlate gender in terms of M and Fs because we won't be able to compute any differences. We can't subtract some values, 2 letter values from each other, for instance. Okay, so we're going to leave this as this. I want to point out here that we have some different types of correlations. In SPSS, if you put in a categorical variable, such as gender here, it will automatically compute for you a point by serial correlation, but it will refer to it as a Pearson correlation. So that's a nuance that you might want to know for class, but you don't necessarily need to know for in SPSS. It just will automatically do that for you. So we're going to look at whether or not gender correlates with vocabulary at these different time points. So again, we can see that a lot of this table is redundant from what we looked at before. This 3.48, this or 0.348, this 0.647, and this 0.49 are all things that we've seen before in the previous example. Wait, sorry, it's these values that we've seen before: 0.327, 0.479, and 0.689. because these are the correlations, intercorrelations among vocabulary at different time points. This top row tells us how gender correlates with these different, with vocabulary measured in the number of words, again, that kids know at these different time points. How we interpret this is going to be a little bit tricky because gender here is coded as 0 and 1s. So we need to know how that's coded in order to interpret this. So go back to the table and we can see that when gender is male, then code equals 0. And when gender is female, then code equals 1. So from that, we can say that as you move, and this is a little bit not intuitive, but when you go from male to female, then that value is getting bigger, right? So we can say then that because these correlations are positive, females tend to have higher vocabularies than males. The literature seems to support this, certainly stereotypes seem to support this as well. So sometimes people might argue that there are language delays for little boys, for instance. Okay, so that is represented in this data as well. So gender correlates with vocabulary at time 1.5 years, 2 years, and at 3 years. Okay, with the weakest correlation being at this time, but again, that's not a statistical test of it. You would actually have to do something else to compare the strength of the relationship across these time points, and that's beyond the scope of what we're going to do in this video. All right, so we would report these as point by serial correlations, even though, again, they're mislabeled as Pearson correlations here. All right, and then finally, we can look at the correlations between two categorical variables in terms of a phi coefficient. Okay, sorry about that. So the last correlation that we want to look at is a phi coefficient. It examines the correlation between two categorical variables. And for this, we're actually going to use a different technique, but I would like to point something out to you. The first thing is that SPS is very smart. Sometimes it can be too smart in that it tries to guess what it is that you would like to do. So as you guys move on to more advanced statistics, SPSS might make assumptions for you that you might not want it to make. In this case, actually, the assumption is not bad, but so I'll point that out to you. So here we want to go to, for creating a correlation between two categorical variables, we'll go to descriptive statistics, and then we're going to go to crosstabs, and we'll click that. And then we're going to just put in our categorical variables. So here I put in gender and then mom's education level. And under statistics, I have checked phi and Kramer's V. So we want the phi coefficient, and we can just go ahead and push continue and OK. And so we'll read this very similarly to the previous. We can see here in the crosstabs it tells us how many participants fall into each of these categories. And you can see that it's fairly evenly represented across these categories. So here, mom's education code, this is high school, would be 0. Anything beyond high school is 1, college and graduate school. And then gender code, again, as a reminder, male is 0 and females are 1. All right, so moms who have a high school education who had male children, that's 16. Moms who had a college degree or more with male children is 15. Moms who have high school degree with female children is 14. And then finally, moms with college degrees or greater who have female children is 15. And that gives us 15 participants roughly per cell, but 60 in total. So here there's a little bit of a discrepancy. So here is the correlation that you want to report. So the phi correlation, the phi coefficient, is this value here. So we see that there is effectively no evidence of a relationship. So it's not that women who have one kind of degree, like a high school degree versus a college or graduate degree, are more or less likely to have male or female children. That makes sense that this should be a null correlation or null association. And the p-value here is given by the approximate significance. So the thing I wanted to point out to you guys is if we look at the correlation of these two factors, so gen code and mother's education code, and we run it as a Pearson correlation, we effectively get the same result. So here, the Pearson correlation is a 0.033, and that's actually a phi coefficient. And here, the significance level is reported as a 0.80, which is more or less the same as here. So for the purposes of this class, I'd like for you to run the phi coefficient out of the crosstabs, and you will want to be able to interpret some output that looks like this. Okay, so that's how you would do these correlations for the time being. Next time we'll talk a little bit more about multivariate correlation, and we can move on to regression.